Welcome to the deep dive. Today, we're jumping into something really core to Python. We're talking about its keywords.
Yeah, those fundamental building blocks. You know, that list. False, none, true, and as assert. All the way down to yield. It looks, well, pretty daunting at first glance.
Totally. It feels like this huge list you just have to memorize.
Exactly. And our source material does something really helpful here. It takes all 35 of those keywords and gives us a way to understand them without just brute force memorization. It breaks them down.
Right. So that's our mission today for you listening. Forget the long list. We want you to see the structure, the grammar of Python through just, 9 functional groups.
That's it. 9 categories. We'll walk through things like control flow, data types and values, defining functions and classes,
Okay.
exception handling, imports, how variables are handled, operators, the async stuff.
Right. The newer 2 words.
Yeah, asynchronous programming, and then some important extras like context management. It really provides a map.
Okay. Sounds like a plan. Let's dive right into that map. First up, control flow. This feels like programming 101, right? Keywords for making decisions and repeating things.
Absolutely. You've got your if, elif, else for choosing paths.
Wrenching logic, yeah.
And then for looping, for doing things over and over. But the interesting part is often how you modify those loops.
You mean like stopping early or skipping certain steps?
Precisely. That's where break and continue come in. The source material had a good way of showing this with a list example.
How did it explain the difference? Because sometimes they feel, kind of similar. They both interrupt the loop somehow.
They do, but in very different ways.
Yeah.
So imagine you're leaping through numbers. If you hit a continue, you basically just jump straight to the next number in the list. You skip whatever code was left in that specific iteration.
Okay, skip the current step.
Right. But break, that's the emergency stop. If you hit a break, the entire loop just ends. Done. No more iterations.
Got it. Skip versus stop. Makes sense.
Yeah.
And what about pass? It always feels so weird. A keyword that literally does nothing.
Yeah, it seems counterintuitive, but it's actually structurally necessary sometimes. Python syntax demands something in an indented block.
Oh, okay.
So if you're sketching out code, maybe you have an if statement or a function definition, but you haven't written the logic yet.
You just put pass there for now.
Exactly. It satisfies the interpreter, lets the code run without error, but executes no operation. It's like a structural placeholder scaffolding.
Okay. Moving on from directing the flow. Let's talk about the basic values, the really fundamental ones. True, false, and none.
Right. True and false, those are your Booleans. Pretty standard across many languages.
Yeah, yes or no.
But none. None is special in Python. It trips people up sometimes.
Because it's not 0 or an empty string.
Precisely. It's none of those things. None specifically means the absence of a value. It's a distinct concept. 0 is a number, an empty list is still a list.
That's just empty.
Right, but none means nothing here yet, or no value applies.
So practically, if I have a variable, say user input, and the user hasn't typed anything yet, I'd set it to none initially.
That's a perfect use case. Initialize it to none. Then later, your code can check specifically if user input is none to see if it's still in that unset state. It's much clearer than, say, checking if it's an empty string, which might be valid input itself.
Ah, okay. It signifies intentionally missing.
Exactly. Universal placeholder for missing.
All right, section 2. How do we organize all this code? We need structure. And that brings us to def and class.
Yeah, this is about building reusable blocks. Def is how you define a function. You package up some lines of code, give it a name.
Like def add numbers, x, y.
Perfect example. And often inside that function, you'll use the return keyword to send a result back out.
Right, return x plus y.
Exactly. And then class. Well, that's the gateway to object-oriented programming, OOP.
Defining blueprints for things.
That's a great way to put it. A class is the template, like the dog class example in the source. You define what all dogs will have, maybe a name, a breed.
Methods, like bark.
Right. Methods are functions tied to the class. The class itself doesn't do the barking. It defines how any dog object created from it can bark.
Okay. And then there's lambda, the sort of quick and dirty function keyword.
Yeah, it's the shortcut for simple functions. Lambda lets you create a small, anonymous meaning, unnamed function all in one line.
So not for complex stuff.
Definitely not. You wouldn't write multiple lines of logic in a Lambda. But if you need a quick function for something like sorting, or maybe in a data transformation pipeline.
Like specifying a sort key?
Perfect example. Lambda item 1 to sort by the second element of a tuple. It's concise, very functional, code shorthand.
Cool. Okay, so we've defined functions and classes. Now, how do we bring in code from outside our script?
Yeah.
That's the import keywords, right? Import, from, and as.
Yes, managing Python's huge ecosystem of libraries. Import is the most basic. If you need the whole math library, you just say import math.
And then you have to use math before everything from it, like math.py.
Correct. It keeps things namespaced, clear where pi came from.
But sometimes you don't need the whole library, just one specific thing.
And that's where from comes in handy. If you only need the date object from the datetime library, you can write from datetime import date.
And then you can just use date directly, like date.today.
Exactly. It pulls that specific name into your current scope. Can make code a bit cleaner if you only need one or two things, but you have to be careful not to cause name clashes.
Right, and omorm. That just seems like giving things a nickname.
It is. It's for creating an alias. The classic example everyone uses is import pandas as PED.
Yeah, you see that everywhere.
And it's not just shorter, it's a convention. It makes the code instantly recognizable to other Python developers. Readability and community standard, really.
Okay, let's shift gears to safety nets. What happens when code goes wrong? Like trying to divide by 0. That's the try, except finally block, isn't it?
Absolutely. This is crucial for writing robust programs that don't just crash. You put the code that might fail inside the try block.
The risky stuff.
Right. If an exception happens in there, Python immediately jumps to the except block that matches that error type.
Like except 0 division error.
Exactly. And inside that block, you write the code to handle the problem gracefully. Maybe log the error, tell the user something went wrong, provide a default value.
Instead of just crashing.
Right. And then there's finally, what's its role again? It always runs.
It always runs, no matter what. Whether the try block finished successfully,
Okay.
or an exception occurred and was caught by except, or even if an exception occurred that wasn't caught, the finally block executes.
Ah, okay. So it's for cleanup, like closing a file or releasing a resource.
That's the classic use case. Guaranteed cleanup. The source showed execution finished, printing out even after the error, which really drives home that guarantee.
Got it. Now, related to errors, we also have raise and assert. These seem different.
They are. Raise is how you intentionally trigger an error.
Ah, so you're creating the exception yourself.
Yes. If your function expects, say, a positive number and it gets a negative one, you might raise value error. Input must be positive. You're enforcing the rules of your code.
Okay, so raise is for enforcing contracts. What about assert? That feels more like checking things.
It is. Assert is primarily a debugging tool. You wrote assert followed by a condition that you believe must be true at that point in the code, like assert count 0, 0.
And if it's not true,
The program stops immediately with an assertion error. It tells the developer, hey, your assumption right here was wrong. It's great for catching bugs during development, but usually you don't leave assertions enabled in production code because they could be turned off globally.
okay, so raise for runtime errors you anticipate handling, assert for debugging checks. Makes sense.
Now, variable handling. Delin just seems pretty straightforward, just deleting stuff.
Yeah, Dells removes a name binding. You can delete a variable entirely or remove an item from a list like del mylist1, freeze up the name or the item. Simple housekeeping.
But then we get to global and non-local. These always seem to cause confusion, especially non-local.
They do, because they deal with scope, which is about where Python looks for a variable.
Right, so global. When do I use that?
You use global inside a function when you need to modify a variable that was defined at the very top level of your script, the module level, the true global scope.
And if I don't use global and just assign to a variable with the same name inside the function,
Python assumes you're creating a new local variable inside that function. It won't touch the global one. Global explicitly says, no, I mean the one outside.
okay, so where does non-local fit? It sounds similar.
It's similar but different and only applies to nested functions. So you have an outer function, and inside it, you define an inner function.
Okay, a function inside a function.
Right. Now, if that inner function wants to modify a variable that lives in the outer function.
Not the global scope, but the parent function's scope.
Exactly. That's when you use non-local. It tells Python, look for this variable in the nearest enclosing scope that isn't global. It lets the inner function affect the state of its immediate parent. Crucial for things like closures.
Ah, okay. That nesting is the key difference.
Yeah.
Global for the top level, non-local for the enclosing function level.
You got it.
All right, almost there. Let's talk operators. We have the usual suspects like and or, not for Boolean logic, but Python elevates two others to keyword status. In and is.
Yeah, in is pretty intuitive. It checks for membership. Is this item present in this sequence, like a list or a string? 2 in my list. Simple enough.
But is the tricky one. It's not the same as double equals.
Not at all. And this is a really important distinction. Double equals checks if the values are the same.
Do they contain the same stuff?
Exactly. But is checks for identity. Are these two variables pointing to the exact same object in the computer's memory?
Okay, so memory location. The source had an example with lists, I think.
Yeah, a great one. If you make list A 1, 2 and list B 1, 2, they look the same, right?
Same content.
So A equals B would be true.
Yeah.
But Python probably stored them in 2 different places in memory. So A is B would be false. But if you then did C equal A, you're not making a new list. You're just making C another name pointing to the same list object that it points to.
So they share the same memory spot.
Exactly. Then A is C would be true. Understanding is versus is key for understanding how Python manages objects and memory, especially with mutable types like lists.
Right, subtle but crucial. Okay, last category. This feels like the advanced stuff. Asynchronous programming with async and await.
Yeah, this is more modern Python, tackling concurrency. Traditionally, Python code runs one line after another, single-threaded.
So if something slow happens, like waiting for a website to respond.
The whole program just waits. Sits
Yeah.
there doing nothing.
Wasting time.
Exactly. Async and await provide a way around that. You mark a function with async def, making it an async function or coroutine.
Okay.
Then inside that function, when you call another operation that might take time, like network I/O, database calls that are properly written to be awaitable, you put await in front of it.
And what does await do?
It basically tells Python, okay, this might take a while. I'm going to pause this function right here, let you go do other work, and let me know when this result is ready.
So the program doesn't block. It can do other things while waiting.
Precisely. It yields control back to the event loop. It
Right.
enables cooperative multitasking within a single thread. It's absolutely essential for building things like high-performance web servers or anything, doing lots of network operations concurrently.
Very cool. And finally, you mentioned 2 others, often just listed as other, but actually really powerful, with and yield.
Yeah, they deserve a spotlight. With is all about context management. It's a way to guarantee that setup and teardown actions happen around a block of code.
Like the file example,
Yeah.
with open.
That's the classic. When you use with open myfile.txt, RSF, Python automatically ensures that file F gets closed properly when you exit that block. Even if an error occurs inside the block, it's automatic resource management. Super safe.
Okay. Handles the cleanup reliably. And yield.
Yeah.
That's related to generators, right?
Yeah.
Memory efficiency.
Hugely important for that. Think of return a function. It sends back a value, and the function is done. Its state is gone.
All right.
Yield is different. When a function hits a yield statement, it sends back a value, but then it pauses its execution right there, preserving its local state.
It remembers where it was.
Exactly. The next time you ask it for a value, it resumes right after the yield, runs until it hits another yield, or the end, pauses again, and so on. This creates a generator.
And why is that useful?
It lets you work with potentially massive sequences of data, even infinite ones, theoretically, without loading everything into memory at once. You generate and process one item at a time. Incredibly memory efficient for data pipelines, processing large files, things like that. Yield is really powerful.
Wow. Okay, so we went from that intimidating list of 35 keywords
Yeah.
to seeing them grouped into these 9 logical roles. Control flow, definitions, imports, error handling, scope, operators, async. It really does feel like a map of the language's grammar now.
It really does. These are the fixed rules, the reserved words Python uses to understand structure. And getting comfortable with the nuances, like we discussed, is versus R, or when exactly non-local is needed instead of global.
Yeah.
That's what really makes a difference. It speeds up development because you're speaking Python's native language fluently.
Definitely less mystery, more system. So to wrap up, here's something to think about. We touched on those specialized keywords near the end. Yield, async, await. Consider how these specific words aren't just commands, but tools that fundamentally change how Python executes. They let it handle complex flows, manage resources efficiently, and juggle tasks concurrently. How does having this kind of power built right into the core vocabulary allow Python to go beyond simple scripts and become the engine for really complex, large-scale systems?